We don't understand it. Not initially. So what's your first thought? Is it aliens? That could be. Like I said, it's not my first thought. I promise you, it will be my last thought, but it's not in the list. It's in the list. It's just way down based on the history of trying to understand things that we don't understand. We have 2 more objects that have come through, and they have some weird properties. The brightness, the rotation rate, and so they don't match some of our models for what comets and asteroids should do.
So why should unexplained brightness and rotation in newly found interstellar objects push us to revise natural models before invoking technology? What counts as an explanation in astronomy, and how do we rank possibilities? An explanation is a set of causes that, when applied to known laws, predicts the observation. Ranking possibilities relies on prior probability, which means how often a cause has worked for similar cases in the past. The foundational assumption is that physics is uniform. The same gravity, radiation, and thermodynamics apply everywhere, unless evidence shows otherwise. Gravity, sunlight, and heat are universal drivers, and they account for the bulk motions and appearances of small bodies, which is observationally established across comets and asteroids in our solar system. We also assume measurement error and selection bias can shape what we see. Selection bias means our instruments and methods preferentially detect certain kinds of objects. Given these premises, we test ordinary forces first and treat engineered causes as last resort explanations because they have lower prior probability without direct signatures. And the near-term result is a disciplined path. Start with gravity and light, then add material properties, then consider rare natural processes, and only then examine technological hypotheses. What exactly is an interstellar object, and why might it diverge from our local expectations? An interstellar object is a small body that is not bound to our sun and passes through on a one-time hyperbolic path. Its surface has likely experienced different chemical and radiation histories than local comets because it formed around another star and drifted for millions of years in interstellar space. Cosmic rays, which are high-energy charged particles, can alter and harden surface layers by breaking molecular bonds over long times, which is theoretically well studied and lab-tested on analog materials. Thermal cycling near different stars can deplete some ices while leaving others trapped under a crust, so a distant heating event could trigger gas release in surprising ways. Observationally, discovery surveys are tuned to moving points of light against a crowded star field, so we preferentially notice objects that are either unusually reflective or cross our sky with a distinctive motion. These conditions mean the first interstellar visitors we detect will likely be the ones that are easiest to spot, not the ones that are most typical. The synthesis is that interstellar origin plus detection bias makes it reasonable that early examples will look odd relative to our comet textbook. How can a small body change speed or direction slightly without an engine? A non-gravitational acceleration is a tiny push not caused by gravity, often arising from outgassing or radiation pressure. Outgassing means sunlight warms an ice, the ice sublimates directly to gas, and the gas jet exerts a thrust. This is observationally established for comets through visible comae and jets. Radiation pressure is the push from sunlight on a surface. It is weak per unit area, but if an object has a large area compared to its mass, the effect can be measurable. The Yarkovsky effect is a thermal recoil force. A rotating body re-emits absorbed sunlight as heat slightly later in time and in a preferred direction, producing a small thrust. It has been measured on certain asteroids in our solar system. The absence of a visible coma does not exclude outgassing if the release is dust poor, such as sublimation of carbon monoxide, carbon dioxide, or even hydrogen, which could be too diffuse to scatter sunlight strongly. This is theoretically suggested and consistent with low dust signatures. Alternatively, a highly porous, low-density aggregate could experience stronger radiation pressure than a compact rock of the same size because area-to-mass ratio would be higher. This is physically straightforward. The concise point is that sunlight and volatile ices can generate small, steady pushes that look like controlled motion but require no technology. Why do brightness changes and odd rotation not imply artificial shaping? A light curve is the pattern of brightness over time as an object rotates. It reflects changing cross-sectional area and surface reflectivity, called albedo, seen by the observer. A tumbling state is a non-principal axis rotation, meaning the body spins around a wobbly combination of axes rather than a single stable one. This occurs naturally after uneven outgassing or collisions and can last for years in low-friction rubble piles. Large amplitude light curves can arise from elongated or flattened shapes, but they can also come from strong albedo variations. Dark regions absorb light and bright regions reflect it, making the object brighten and dim without extreme geometry. The observed lack of periodic stability can be explained by ongoing torques from asymmetric heating or sporadic gas release, which disturb a previously steady spin. This is a known mechanism on comets. Surface roughness and facets can create sharp changes in reflection at certain viewing angles, increasing variability even if the object is not razor-thin or needle-like. The takeaway is that complex brightness and rotation behavior emerge from ordinary shapes, materials, and spin dynamics once we account for surface properties and external torques. Why do we find the unusual ones first, and how does that skew interpretation? A detection threshold is the minimum brightness or motion a survey can pick out above noise, and near that threshold, only the most conspicuous objects are found. Malmquist bias is the tendency to oversample brighter objects in a flux-limited survey. It is a well-known statistical effect in astronomy. For fast-moving visitors, survey pipelines may flag them precisely because their motion stands out. Even if slower, darker objects are more common but remain below detection limits. An object with higher reflectivity, or with a rotational state that occasionally presents a large reflecting area, could momentarily cross the threshold and be discovered, while more typical bodies pass unnoticed. High area-to-mass objects are also overrepresented if they get a small radiation pressure boost that keeps them in the detectable field longer or makes their motion distinctive enough to trigger follow-up. The microsynthesis is that our early sample is not representative by design, so outliers appear first and look puzzling until our data set broadens. What would distinguish an artifact from a natural body? And what do current observations show? An artifact is an engineered object that exhibits signatures inconsistent with passive physical processes, such as controlled trajectory changes, engineered materials, or information-carrying emissions. Clear differentiators would include narrowband or deliberately modulated radio signals coincident with the object, which targeted searches have not detected. This is observationally established by dedicated radio follow-ups. Spectral features indicating metals in manufactured forms, polymers, or layered coatings would suggest fabrication, but spectra to date are consistent with space-weathered ices and minerals within current uncertainties. Maneuvers that contradict all known passive forces, such as accelerating against sunlight or changing course and shadow without outgassing, would be strong evidence, yet recorded accelerations align in direction and scale with sunlight or plausible volatile release. Thermal behavior that maintains tight temperature control independent of illumination would imply active regulation, which has not been seen. In summary, the data fit challenging but natural interpretations, while engineered signatures are absent. So, the answer to our opening question is, because the combination of uniform physics, interstellar surface histories, and strong detection biases makes unusual brightness and rotation the expected frontier case for natural models, and invoking technology only becomes rational when positive, diagnostic evidence of engineering appears. Like if this was interesting, and hit the subscribe for more.